class, we want to talk about how to balance redox reaction. Okay. Now, redox reaction is basically the reactions that do take place inside electrochemical cells. Right? Electrochemical cells are comprised are made up of electrodes, the anode and the cathode. Now, be it electrolytic cell or the galvanic cell, the anode is actually an electrode where oxidation do take place, and the cathode is actually the electrode where reduction do take place. And both the anode and the cathode can be found in both cells. So the reaction that takes place at the anode is called the oxidation. The one that takes place at the cathode is called reduction. So when you combine both of them together, it rise to what we call redox reaction. So this redox reaction here is actually two words that is joined together: reduction and oxidation reaction. All right, so one of the major questions that normally appears in the exams is actually redox reaction. So let's quickly run through redox reaction. So we said redox reaction can be balanced in the following medium: either in the acidic medium or in the basic medium. Most of the times, you are going to be told which of the medium that particular question is under. But what if you're not told? What if they just give you a question and you're asked to balance the following redox reaction? Now, if you're not told whether it is acidic or basic medium, you can choose any of the medium to make use of, right? Any of them. At the end of the day, we're going to get the correct answer. So look at this. The first rule we have, rule number 1. Now, you're going to divide the equation into two half cells. If you could recall, there are three major ways one can balance chemical equation, right? We have the inspection method, basically the method that involves staring at the equation and then, coming up with coefficients to add up to balance it up. We have the second guy, algebraic method. And then we have the third guy, half reaction method, if you recall. Now, half reaction method is used mostly for redox reaction. So that's why we say, in rule number 1, you have to divide the equation into two half reactions using the oxidation numbers. Right? I'm going to give us a brief explanation of oxidation number. Now, the next rule says balance atoms other than oxygen and hydrogen. That means that once you've succeeded in dividing the two half reactions into two, the reduction half cells and the oxidation half cell, the next thing you're going to do, balance them individually. So you go to oxidation half cell, check for atoms other than oxygen and hydrogen and balance it. Go to reduction, do the same. Now, the third step says balance oxygen by adding 1 molecule of water for every oxygen that is needed. So for every oxygen that is needed, you're going to add 1 water. If I need 2 oxygen, I'll add 2 molecules of water. Now, 1 molecule of water is written as H2O because this guy contains 1 oxygen atom. So if you need 1 oxygen, you're going to add 1 water. If you need 2 oxygen, you increase the molecules to 2. Now, rule number 4 says balance hydrogen. Sorry, hello. Can you guys reduce the noise? Okay? Please. I can use MD1 or upstairs. So we said rule number 4, balance hydrogen by adding hydrogen ion. Of course, if you add water to balance oxygen, you have ended up introducing what? Hydrogen. So for me to balance the added hydrogen, we're going to use hydrogen ion. Now the next one says, once you're done with the atoms, right? You're going to balance the atoms. Once you're done, you move down to the charge. Balance half reactions electrically, because for any redox reaction to be balanced, we have to look out for 2 things. The first one is that, are the atoms balanced or are the elements balanced? The second guy is that are they balanced electrically, right? So rule number 5 says balance half cells electrically by adding electrons to the side that is more positive. Of course, I'm going to explain it shortly. The last but not the least says use a coefficient, all right, to ensure that electron gain, this electron gain is always in reduction half cell, right? Is equals electron loss in oxidation half cell because oxidation is loss of electron and reduction is gain of electron, right? So having said that, we're going to take some few examples. Now look at this. Balance the following reaction in an acid medium. How do we go about this? Now, first thing first, rule number 1 says you have to divide this equation, that's redox equation, into two half cells, the reduction and the oxidation half cells, so that you can actually balance them individually. Once you're done, you combine them together, you join them together. Now, but for us to be able to split this guy into two half cells, we must actually understand the concept of oxidation number, right? Now, oxidation number, so in this case now, oxygen is always having -2. Let me just give us a few rules for oxidation that will help us here. Number 1 is that oxidation number of any element that is uncombined, oxidation number of any element that is uncombined is always equal to 0. Uncombined means you see something like this. Uncombined of three elements. In as much as this guy is mixing up with himself, but this is considered uncombined because he's not combining with any other element. So this guy is going to be 0, this will also be 0, and of course this will also be 0. Now the next guy I would like us to pay attention. Oxidation number of a monoatomic ion. Oxidation number of a monoatomic ion simply refers to as an ion, just a single atom that has either a negative charge or a positive charge. For example, if I have something like this, oxidation number of this guy is actually -1 because this guy is just a single atom. Or perhaps I have Na plus. Now this is going to be +1 because this guy has a single atom. So oxidation number of a monoatomic ion obviously is a charge of the ion. Now the number 3 stuff is that oxidation number of oxygen is always -2, except in peroxides. Peroxides, of course, I'm referring to the most common example, except in this compound, except in hydrogen peroxide or in peroxide compounds where oxygen is going to have a -1 oxidation state. Now, apart from this compound, oxidation state of oxygen is always -2. Okay, so these are the three. Hydrogen, oxidation number or oxidation state of hydrogen is always +1. Oxidation number of hydrogen is always +1, except when hydrogen combines with a metal. Except when hydrogen combines with a metal, in brackets, hydrate. If hydrogen combines with a metal, hydrogen in this case will be acting as a non-metal. Right? That means hydrogen will be accepting electron. It's going to be negative. But if hydrogen is actually reacting with non-metals, like other chlorine and the rest of them, they act as a non-metal, they share their electrons. Right? So these are the last but not the least for this is that now what if in a compound that contains multiple atoms, like in this case now, this guy contains multiple atoms, and I'm asked to find oxidation number of chromium here. Now this is what I'm going to do. Oxidation number, sum of oxidation number in a neutral compound. I repeat, sum of oxidation number in a neutral compound is always equal to 0. Neutral compound example is AMnO4. So if I want to solve for manganese, let's assume I do not know the value of manganese. For potassium is in group 1. Oxidation number of all elements in group 1 is always +1. Oxidation number of all elements in group 2 is always +2. Please take note of this. Potassium is in group 1, so this guy is going to have plus 1. Why did I say it's plus 1? Because potassium belongs to group 1 of the periodic table, and all elements under the group 1 will have plus 1 oxidation state. All elements under group 2 will have plus 2 oxidation state. So this guy is plus 1. Manganese is X. I do not know manganese. Oxygen is minus 2 times 4. Now you have to equate it to 0 so that you can solve for this X. Now, why am I equating it to 0? Because this guy is a neutral compound. But in the case here, this guy is a charged compound. If it's a charged compound, I will equate it to what? Minus 2. So having said that, we're going to use the concept to solve for this. Alright? Alright, please look up. Now having done that, let's split this equation into two half cells. That's rule number 1. We want to have our reduction, and we want to have our oxidation. So let's go ahead to split it into two half cells using the oxidation number. Please look up. Oxidation number of this guy here would be minus 1, because this guy is a monoatomic ion. Oxidation number of iodine here will be 0, because this guy is uncombined or element in a free state. So you notice that something moving from minus 1 to 0 is actually an increase in value, because 0 is greater than minus 1. So an increase in oxidation number is oxidation. Decrease in oxidation number is what? Reduction. So if you notice, this guy initially was minus 1. It moved from minus 1 to 0, which shows there is an increase. An increase in oxidation number is oxidation reaction. So therefore, I'll come here and say this was what actually oxidized. Moved from minus 1 to 0. So this is my oxidation half cell. Now look at this. Let's solve for chromium. I'm not going to solve for oxygen here, because oxygen actually is not in the product side. And not just that, oxygen is always having a constant oxidation number, except in peroxide. So what we are going to solve for is chromium. Now, how do we solve for oxidation number of chromium? I'll say make chromium to be X. Make chromium to be X. So this becomes 2X. Because I do not know the value of chromium, I want to solve for chromium. I will assume chromium oxidation number to be X. But chromium is appearing 2 times here, 2X plus. Oxygen is always minus 2. Now, how many oxygen do we have here? Times 7 equals to the charge of this compound, which is minus 2. This becomes 2X minus 2 times 7 is minus what? 14 equals to minus 2. 2x equals to minus 2. Now, when this minus 14 crosses over, it becomes what? This becomes 2x equals to 12. Right? Now, so therefore, my x equals to 12 over what? Now, which is what? So, oxidation number of chromium here is plus 6. Now, what is chromium here, class? Plus 3. Because I just told us that oxidation number of a monoatomic ion, right? Atom that is standing on its own and is actually having a charge. So this guy will be what? If you notice, is there a decrease in oxidation number or an increase in oxidation number? Decrease. Something moved from plus 6 to plus 3. That means there is a decrease, right? So that is reduction. Is it also? So we'll come here, we'll say Cr2O7 minus so we are done with the first step. We have succeeded in actually splitting this guy into two half cells. Step 2. Class, step 2 says balance atoms other than oxygen and hydrogen. We're going to do that for each of the half cells. Now, let's start with this guy. So I'll come here, I'll rewrite this reduction, come back here, oxidation. I'll put Cr2O7 2 minus, giving me Cr3 plus. Now let's complete the reduction before we move down to the oxidation. Now let's leave out oxygen and hydrogen. Anyway, you see oxygen, just ignore it. We're going to treat oxygen in step 3. For now, apart from oxygen, which other element do we have here? Chromium, right? So let's balance this guy. On the left hand side, chromium is 2 here, right? On the right hand side, chromium is how many? 1. So we need to balance chromium, it's not. So we put what here? 2. So by so doing, I've actually balanced chromium. So I move down to the next guy. Of course, there is no oxygen, no hydrogen here. We have iodine. So if you want to balance this iodine, on the right hand side, we have 2 here. Is it also? On the left hand side, we have how many? 1. So if I want to balance this guy, I'll put 2 here. Step 2 is done. So we've succeeded in balancing atoms other than oxygen and hydrogen. Now the step 3. Step 3 says balance oxygen by adding 1 water for every oxygen that is needed. So if I need 1 oxygen, I'll add 1 water to the opposite side. If I need 2 oxygen, I'll add 2 water to the opposite side. So now let's rewrite this guy. From 2, we move to 3. So from this guy, we have my reduction here. We have Cr2 O7. Now look at this. Let's balance the reduction before we move down to the oxidation. Okay, let's go. Oxygen on the left hand side is how many here? 7. Is there any oxygen on the right hand side? No. Remember, for every 1 oxygen that is needed, we have to add how many water? 1. So if you are needing 7, how many water are you going to add? 7. So you got the same plus 7 water. Now, let's look at the oxidation. Now, the oxidation is 2I. Now, there is no oxygen here, is it also? There's no oxygen here. So move down to step 4. Bear in mind, guys, I can still do this in just 1 line. I'm doing this because I'm trying to explain. Subsequently, I can decide, okay, the next example I'm going to take, I'll use just 1 line for all of them so that I see I can do what. Step 4 says, balance hydrogen by adding hydrogen ion. Now, look up. So let's write this guy. All right, look up. The reduction half cell have hydrogen, whereas the oxidation do not have. And he said for every hydrogen that is needed, add hydrogen ion. So now look up. In this reduction half cell, on the left hand side, there is no hydrogen, is it not so? On the right hand side, we have 7 times 2. 7 times 2 is how many? 14. So we have 7 times 2, which is 14. Which means that on the left hand side, we're going to add 14 hydrogen ion to balance this guy. This becomes plus 14 H plus. Because 7 times 2 was 14. So we need to balance this entire hydrogen by adding 14 hydrogen ion on the opposite side. Now there's nothing to do here, is it not so? So step 5 says balance them electrically. So let's complete step 5 here. Now look at this. Let's balance this guy, then we'll look at the next one. This guy says balance it electrically by adding electrons to the side that is more positive. Now, look at the left hand side. The left hand side of this guy, we have minus 2 here. We have plus 14. This is a plus here, right? Plus 1. 1 times 14 is 14. So minus 2 plus 14 will give us what? Plus 12. It's more like saying 14 minus 2. Right? So the left hand side is giving us plus 12. Now the right hand side is 2 times 3 is what? Plus 6. Right? 2 times 6. So between plus 12 and plus 6, which of these is more positive? Plus 12. So our aim is to reduce this plus 12 to be like plus 6. So how many electrons will I add to 12 to reduce it to 6? It's 6. So you come here and say plus 6 electrons. So that's how we got that guy. Now we move down to the next one. Now we have 2 minus. Now, if you look at this guy, the left hand side, 2 times minus 1 minus 2. The right hand side, elements that are not combined states, there's no charge, so it's 0. There's no charge here, so this guy is neutral, it's 0. Now, 0 and minus 2, which of these is more positive? 0. So, how many electrons will I add to 0 to reduce it to minus 2? It's 2. So, I'll come here and say plus 2 electrons. All right, so let's start step 6. Step 6 says use coefficient to ensure that electron gain is always the one on the reactant side of the reduction. It's equals to electron loss. So here is 6 and here is 2. Now this, since they are not the same, electron gain is 6, electron loss is 2. Now ask yourself, what can I multiply with the smaller value to equate it to the bigger one? Here is 6 and here is 6. So what I'm going to, I will inverse multiplication. I'll multiply this here by 3, not really inverse. I'll multiply this here by 3, I'll multiply this here by 1. So that 3 times 2 will give us what? 6. But what if this place here is 3? Or this place will be 3. Now in this case now, there is no whole number that can multiply with 2 to give us 3, right? So what I'm going to do is I'm going to do opposite multiplication. Use this 3 and multiply 2. And use 2 and multiply what? So that we all have 6. Is it not so? But since here is 6, there is a whole number I can multiply with 2 to give me 3. So this becomes we multiply this here by 3. 3 times 2 will give us 6. 3 times 1 will give us 2, and 3 times 2 will give us 6. So you notice that electron gain is now equal to electron what? Loss. So what we're going to do now, alright, so this becomes reductant plus alternate equals redox. Let's get our redox reaction back. So what we are going to do is that we're going to cancel the electron. 6 on the left hand side, cancel 6 on the right hand side. Now let's bring down CR2O7 2 minus plus now this is overall equation. How do you get this? You bring down what is on the reactant side. CR2O7 2 minus is on the reactant side, bring it down. 6I minus is on the reactant side, bring it down. Now 14H plus is also on the reactant side, bring it down. Now moving on to the product side, this guy is on the product, you bring it down. This guy is on the product, and of course the water is on the product. So this becomes the balanced chemical redox reaction for that guy. Now it's a balanced flame redox reaction that took place in an acid medium. So I just want to use 3 lines to balance this guy. So I'll say the first line, and this is a reduction, and then the balanced redox. So that's what I want to do now. First, let's use our oxidation number to split it into 2 half cells. Now iodine here is 0 because elements in an uncombined form is 0. Iodine here is plus 5. Now how do I do this plus 5? Now if you solve for oxidation number of iodine, if you make iodine to be x, that is iodine is always plus 1. Iodine is x plus oxygen is minus 2 times 6 times 3 equals to 0 because this guy is actually a neutral compound. So this is 1 plus x minus 2 times 6 minus 6 equals to 0. X equals to this plus to the this side. So iodine is plus 5. Nitrogen is also plus 5. You use the same concept. Make it be x. So this guy is plus 5. Nitrogen here is plus 5. Oxygen, just ignore because oxygen is going to be -2 everywhere here. None of these compounds are actually peroxide. Nitrogen here is +2. Now, how did I know it's +2? NO, make X subject to the formula. Now, oxygen is -2 equals to 0. X equals to +2. So, having done this, now let's please look up. Let's make this react. Now, iodine is actually moving from 0 to +5. That is an increase in oxidation number. Is it also? Increase in oxidation number is a reduction of oxidation. So I'll come here, I'll put, sorry, this is oxidation. So I'll come here. From 0 to this is oxidation. Ox. All right, so I'll come here, I'll say I2 giving me this. Don't write yet because I'm going to be keeping space. Remember, I'm going to be adding things here. See that we have just hold on. I'm not going to clean the board. I just want to do everything there. Just pay attention. That's the most important stuff. Now, nitrogen moved from +5. Nitrogen moved from +5 to this guy. Decrease in oxidation number is reduction. Something initially was 5. Now, finally, it's now 2. That means there is a decrease in oxidation number. And this becomes, come there and say H, NO3, give me NO. Now, this water here did not take part in any of this half cell. Now, this is actually what you're getting. It's either you ignore the water, bearing at the back of your mind that since this guy is acidic medium, water will always find its way back. Because water will always find its way back also. Yeah. It's either you give us water or if you must add water here, which side will I add water? Physical. What is on? Look at these two half cells. You cannot add water to this oxidation because the component of water is hydrogen and what? Oxygen. Now, looking at the left hand side, there is no atom of oxygen or hydrogen on the left hand side. So if you put it here, what is giving rise to that water from this guy? Nothing. But however, if you put it here, the left hand side has hydrogen and also have water. If you must add the water, you add it to what? Reduction. Is it not so? Well, I'm just going to leave it out. So we are done with this guy. Step 2 says balance atoms other than oxygen and what? Hydrogen. Apart from oxygen and hydrogen, you have nitrogen here, right? Nitrogen is balanced here because it's 1-1. Now let's try the second guy. Now, iodine is not balanced here. Iodine is 2 here, iodine is how many here? So for me to balance iodine, how many will I add here? 2. So I'll come here, I'll put 2. Step 2 is done. Step 3 says balance oxygen by adding water. For every 1 atom of oxygen that is needed, you add 1 water. Now look at this. Look at the reduction plan. Left hand side, we have 3 oxygen. Right hand side, we have 1 oxygen. Meaning that the right hand side is lacking how many oxygen? 2. Right? Now, if it is lacking 2 oxygen, how many water will I add there? 2 water. So I'll come there and say plus 2 water. I repeat, how did I get that 2 water? Oxygen on the left hand side is 3. Oxygen on the right hand side is 1. Meaning that this guy, the right hand side, is actually lacking oxygen. And how many? 2. So for every 1 water, for every 1 oxygen, you add 1 water. So for 2 oxygen, I'll add plus 2 water. And let's do that here. The right hand side has 2 times 3, 6 oxygen, right? The left hand side has no oxygen at all. Can you see that? There is no oxygen here. So the left hand side of this oxidation is lacking oxygen, 6. So how many water are we going to add there? 6 water. So I'll say we are done with step 3. Step 4 says balance hydrogen by adding hydrogen ion. Balance hydrogen by adding hydrogen ion. So let's start the reduction. The product cell has 2 times 3, how many? 4. 2 times 6, 4, right? On the reactant side, there's already 1 here. So that means how many hydrogen is lacking on this side? 3. So I'll come here and say plus 3 H plus. Alright? Now I'll balance my hydrogen. Now let's look at this guy. Hydrogen on this side is 6 times 2, how many? 12. There is 2 here already. So how many will I add to this side to make it 12? 10. So I'll say plus 10 H plus. Now, number 5 says balance them electrically. Now, let me write this far away. Alright. Now, for us to balance this, don't forget the rule. The rule says look out for the ones that is actually the side that is more positive. Add electrons to there. Our aim is to reduce that more positive side to be the same as the other side. So if you look at this guy, the reactant side has 3 times plus 1, that is what? Plus 3. The product side has none, right? Not 0. So in this reaction, which side is more positive? The left hand side, right? Please look up reduction, 0 here, plus 3, giving rise to 0 plus 0. So you realize that on the reduction half cell, the reactant side is more positive by 3, right? The product side is having 0 charge. So we need to reduce this plus 3 to 0. How many electrons are we going to add here? 3. So I'll say 3 electrons. Please, I just had to write this and I wrote it down here so that it's not going to affect our stuff. But normally in exams, you was write it here. Okay. Now let's look at that of oxidation half cell. Reactant side is having 0 charge. 0, 0. Product side is having what? 10 plus. So the question now is, for me to reduce this 10 to 0, how many electrons will I add here? 10. That will say plus 10 electrons. Alright, please look up. Like I said, pay attention. Now the last rule says use coefficient to ensure that the electron gain. Let me rewrite this guy and put the electron on this side. Let me remove the electron here and say plus 3 electrons. Alright. Now the rule says use coefficient to ensure that electron gain is equal to electron loss. Class, we have 10, we have 3 here and we have 10 here. This is what you're going to do. Is there any whole number that can be added, that can be multiplied with 3 to get 10? There is no whole number. There is none. So in the absence of a whole number that can multiply 3 to give us 10, we're going to do opposite multiplication. The one that is 3, multiply by what? 10. The one that is 10, we multiply by what? 3. So this is going to be multiply reduction half cell by what? By 10, and oxidation half cell by what? 3. Now, why are we doing that? The sole aim is to make sure that this guy and this guy will be what? The same. So when I do that, you multiply this guy, 10, there is 1 here, right? 10 times 1 is what? 10. 10 times is what? 30. 10 times 3 is what? 30. So we also have, now this becomes 10. It becomes how many? 20. Multiply this guy by 3. This is 3. This is how many? 18. And this is how many? This is how many? And this is how many? So now, we can see that electron gain, which is 30, is equal to electron loss, which is also what? Now it's time for us to cancel out what needs to be cancelled out and present our final reaction. So let's have this. So first, This cancels out. Now let's look out and see if there are things that also appears on both sides before we finalize. H plus on the reactant side is 30, right? We also have H plus on the product side of this guy, right? So they must cancel out since they are the same. Because they will subtract. You cannot have the same on opposite side, the same amount, and leave it like that. You collect like terms. 30 here, this 30 is on the reactant side of reduction. This 30 is on the product side of what? Oxidation. So they will cancel out. Cancelling out is equivalent to subtracting them. Now look at what I get. What on the reactant side of oxidation is having? On the product side of reduction is having. Now since they are not the same amount, I'm not going to cancel out. I'll subtract. If 18 to subtract from 20, what will be left? Now which side are you going to write it to? The side that had 20. Because this guy had 20 and you take away 18 from it, you're going to be leaving it behind with how many? 2. So you're going to put 2 on the product side. So this is more like saying this cancels this, and this becomes how many? 2. So let's put this down. So our redox reaction becomes 10 HNO3 plus 3I2 Don't forget that this guy is 2 here, right? This equation is balanced. Life and the rest. So in exams, you don't have to, those previous steps I did was just show us the step-by-step procedures. In exams, you can just use one step. Be keeping spaces. You can use your pencil first, so they can clean and write. But make sure you're keeping spaces. Don't just write and join. Make sure you keep space. Because if you use biro to write it and then you may not be able to cancel it out. Alright, so we're going to move straight to basic medium. So before, let's see what we must cover this next.